Here we go. We're going to start off with phase A here, the free body diagram for phase A. So at this point, we've got our little rocket, and we kind of did this one yesterday where we've got a force holding it down, right? That's gravity. And then we've also got a force that's causing it to rise, right? We're going to call that thrust. Going to be much, much higher than mg. All right? So those are your forces that are going on there at the beginning. And by looking at those two forces, we can determine what the net force is going to be. So that weight is going to kind of take away from the thrust ever so slightly, but that net force is still going to be pretty huge. And once we have that net force, we can find the acceleration using F equals ma. Okay, so that's for that portion A. A free body diagram should look something like this. You'll probably have numbers in here, thrust equals, mg equals, and then do that kind of math. All right, phase B, where we are out of fuel, but we're coasting, and we're coasting as we reach the apogee. The apogee is the highest point of its flight. That's number 2. Okay, so between number 1 and number 2 is phase B, and there we're in free fall, right? The only thing that's acting on this rocket here should be mg. Part C, we're still in free fall, but we've paused at this high point because it's got no velocity there, so it hesitates, just like all the projectiles we studied. So this is a good place to break it up, the apogee. So now we're on C, where we're still in free fall, but we're coming down. So our free body diagram here is going to look pretty simple as well. Now in part D, there's going to also be a parachute, right? And so that parachute now is causing drag. So during the rest of this falling part here, D, it's no longer in free fall because there's this drag acting on it as well, right? That's a kind of form of friction. So drag, because it's air resistance, depends on the velocity. And so the greater the velocity, the more the drag force slowing it down. And that happens until the drag force and the mg are equal. So we don't have to worry about that transition, that point like just after number 3, where it's changing its velocity. We're really just focused on the point of part D where it's in terminal velocity. Okay, terminal velocity just means constant velocity. So I'm just going to write that down here. All right. So we know that the magnitude of drag and mg are equal. In other words, the net force is 0, which means that drag plus mg are 0. Another way we could write that is if we're using absolute values, drag equals mg, and I would put the absolute value symbol around mg. Okay, so the value of mg equals the drag, and that's going to be important to us in just a few minutes. Okay, quick little disclaimer here. I realized that I kind of changed my notation from the beginning to the end, from A to D, and there's a reason for that, but I should be consistent. So here we had thrust, it's plus mg, but mg is in the opposite direction as thrust, so I put the negative sign there. That's still true here, okay? So we can say that there's no net force, so that drag minus that mg value equals 0. So when we put those together, we still get this value. We can swing that mg over, we can swing the drag, and then multiply everything by -1, and so we end up with the same statement that drag equals mg. Okay, so for part C yesterday, when we were talking about that, we said that there's a timer, kind of a fuse inside the rocket that goes for 4 seconds from when it's out of fuel until it ejects the parachute. Okay. What I want you to do for part C is assume that that 4 seconds starts here at point 2 and extends to point 3. So we're going to say that that's the time where there's a 4-second interval. Okay, so for part C, you can assume that delta t equals 4 seconds. That's not exactly true, but we're going to just idealize it to make the math easier. Okay, so you've got that time for part C as 4 seconds. So when you're doing the kinematics, you're going to put 4 in for the amount of time there. Okay, so for part D, we just said that we have that statement that drag is going to equal the absolute value of the magnitude of mg. And there's something you have to know about drag. Drag, there's a whole equation to it. I'm going to kind of work it through for you so you don't have to come up with any of this information yourself. But the drag, C sub D is the drag coefficient. In other words, how much does the parachute slow us down? All right, so parachutes can be shaped differently. Some of them have a hole in the middle. If the parachute doesn't open, it's not really dragging very much. So that CD can change. We're going to make an assumption here that our drag coefficient for our parachutes is going to be 1.75. Okay. R is actually going to be the density of the air. 1.3? Yeah, 1.3 kilograms per cubic meter. All right, V squared we're going to take a look at later. That's your velocity. The A is the area of the parachute. So you don't have to do that calculation. I did it for you guys. That's the area. All right, we know what 2 is, and we know that the drag equals mg. So what we'll do is we'll rearrange this to solve for V, and that'll tell you your velocity during this recovery stage. So how hard is it going to hit the ground? All right, so it'll drift down. It won't accelerate down like it would if it were in true free fall because it's got that parachute slowing it down. All right, to throw back to earlier, when we made that correction about drag equals mg, right, it was negative, but when we work the algebra out, we end up with drag equals mg. So those are the magnitudes, right? First of all, that keeps our mg underneath the radical as a positive. But it really, at the end of the day, almost doesn't matter because we're taking the square root. We're trying to find a vector value, velocity, but we're taking the square root. So that means it's going to be plus or minus that value. And so we have to take into consideration when we know that this parachute is slowing our descent. And so we know we're going in this downward direction. And so we're going to choose that velocity to be a negative velocity. All right, so we kind of have to rely on our story here to figure that out. And we just saw in that drag equation that this more surface area, the more drag, right? And so this will try to like slow down if it gets kind of off kilter, right? If it sort of twists itself around, right? If you kind of twist this way, then the fins are going to feel more of that wind coming at it. And so they'll swing back down this way. But then they'll catch this side and they'll swing back this way until they kind of find this equilibrium point right about there where both sides are feeling equal amounts of twist, right? And so that there's a point around which there's called the center of pressure. And we'll make that center of pressure, let's try to make that green. The idea is that we have these fins on the back so that it moves the center of pressure back. Right? If it were just the rocket, then all points would have the same center of pressure, right? The center of pressure and the center of mass would be the same, and so it would just tumble all over the place. But because we have these fins in the back, it shifts that center of pressure back to about here. That's that center of pressure, CP. So that means anytime that this rocket starts to get off kilter, the center of pressure is going to try to like pull back behind the center of mass. All right, and it's going to do that until it's like directly behind. So if that were skewed a little bit though, so if it skews this way, right, then that center of pressure is like a little bit closer to that center of mass than it would like to be because it's feeling that wind. So it pulls it back this way, and that pull is a kind of torque. So let's take a look at how that's a torque. Okay, so when we're talking about torque, we're talking about the application of force that's causing something to rotate. So if I put this force on the center of pressure here, let's say it's pulling this way, right, because that's kind of the direction the wind is traveling. It's going that way. I'll call this drag. And this Cm, in this case, is going to act like essentially our theta. Drag that out. So if we go back to our torque equation until we can make a right angle, torque is the force, right? So it's the angle right here, which we can use R, and we'd say it's sine of theta. okay? So we don't have to actually calculate this or anything, but you do have to understand that the fact that the center of pressure is behind the center of mass and that the drag generated by the fins is what causes this rocket to move straight, or more or less straight. And that's due to two things. First, the pressure of the air against the fins, that's the drag, and the torque that it produces because our center of pressure is behind the center of mass. Okay? That's how torque and pressure apply to our rocket. Okay? Hopefully our rocket isn't like spinning around or anything like that. We're flying in a straight line. But even so, we use torque. We apply the principles of torque to keep our rocket flying straight. Okay. So inside this rocket, we've got an engine. That little engine sits down in the bottom. Excuse me. And it's essentially just a little firework that sticks out the bottom. And then on top of it, it's got this little cap. And it's got something that burns kind of slowly. I'm going to color that in gray. And then at the top, it's got this like really explosive kind of stuff. I'm going to color kind of beige here. All right. So this bottom part, that's the fuel that it burns. And that whole concept of conservation of momentum, right? Remember that at the beginning, nothing's moving. So there's momentum has to be conserved. So in order to get the rocket to go up, this fuel has to be ejected. All that mass has to be shot out the bottom at a really high velocity because it's low mass. So low mass at a high velocity can cause a larger mass to move at a slower velocity, but still pretty darn fast. All right? So that's the first part. Then we've got this fuse that just doesn't burn at all. It just kind of smolders for 4 seconds exactly. And then this orange part explodes. And when it explodes, it applies a force in all directions. All right, and that's from the pressure of the expanding gases. It does actually shoot some of that force down as well. But the downness of that force ends up, because this is such a skinny tube, it bounces back a lot. So a lot of that force is just all pushed against the inside of this rocket. And when that happens, it shoots the top off. So this top part of the rocket pops off because of part of that force. And the parachute and everything inside get ejected. But because that wasn't moving a moment ago, right, that lid was kind of on there, it was part of the rocket, then that means that the rest of the rocket has to recoil and it pushes down a little bit. And so it does two things at once. First, it kind of slows the rocket down a little bit. And two, it causes the parachute to pop out. All right? And we did this a lot more with like cannons and recoil we talked about, right? Or we talked about throwing a snowball when we're standing on the ice, right? We'll slide backwards and the snowball will fly forwards, all right? So that's the idea there. That's in the momentum chapter, we talked about elastic collisions, we talked about inelastic collisions, and one of those inelastic collisions is also called an explosion, where everything has no momentum at the beginning, and then at the end, there's still zero total momentum, but it's two things moving in opposite directions. All right.